constant C which depends only on, I think there is a mistake, that V should be K. V should be K. Okay? So depending only on V, okay, on the set, such that supremum of U over V is less than equal to some C times infimum of U over V. Okay? So for all non-negative harmonic functions U on V. So I am having a bigger domain and I have a compact set. I can take my compact set to be a closed ball which is sitting inside my given domain. Then what it says is that there exists a constant C which depends only on the ball. Okay, so it will depend on R. That's all, radius of the ball. All balls one can, because it's about area. So here we'll have supremum of U less than equal to C times infimum. So the supremum cannot be very large, okay, and infimum cannot be, of course this is a non-negative function, so infimum is anyway going to be greater than equal to 0. Okay? So we have this. And in particular it means this 1 upon C uy is less than equal to ux is less than equal to C times ui. So you are able to compare the value of the function at two different points. Okay? And things do not behave very badly if you are having harmonic functions. You cannot have too much of fluctuations in and I think it should be a good exercise if you are able to show that Harnack's inequality is equivalent to the maximum principle. Just try. The strong maximum principle is equivalent to Harnack inequality. Just try whether it is true or false. Try to write it down. So this is very nice property of. Let me come to the Green's function. Okay, so I am just going to define it over here. So a Green's function for a region. So this function, you see, it is defined for a region. It depends on the domain. It depends on the domain. Okay, it is a function with the property that you have gxy is equal to phi of y minus x minus, that is a corrector function. Phi of y minus x is your fundamental solution. Okay, so if I know what is a fundamental solution, I know fundamental solution I give on Rn, and if I want to solve the problem on a boundary domain, usually we want to look at the Dirichlet condition. We want the function to vanish on the boundary. So the function phi xy is going to be the value of that fundamental solution on that particular boundary. So you subtract it and you get your Dirichlet condition on the boundary. So this is what. Okay. So here one can easily see that it is a symmetric function. Just write down. It is 1 upon mod x minus y power n minus 2, and you can see that. And here this is the representation which Hendrik has used couple of times in his lectures. Okay, so here if u belong to C2 omega solves the boundary value problem, okay, then your ux is given by this. So this is just obtained by your Green's theorem, integration by parts, and you get this particular equality. So this is what he has used several times to represent. See, till now he has you really did not give existence, right? You were just trying to say that if the solution exists, one could write it in this particular form.
Well, I had existence for
Convergence of
penalization.
penalization.
Like I have 80.
I will tell.
What the problem is.
Yeah. So I will tell them maybe. So this is, I'm just telling them the general Green's formula will give give the solution is in this particular form. So you need integration by parts and you will get that the solution. If your Green's function is like this, you get.
I didn't, we're talking about resistance through penalization.
Yes.
And then the motivation part that suggested that we could maybe expand
Yeah, I
it
will.
is through the lower
Base.
semi-continuity.
Yeah, that I will do like this. But that I think is for general lower semi-continuous function, one doesn't need to do it in function space. In
Yeah,
general,
function space is a little bit harder because you need to have the
conditions.
impactness is not easy.
Conditions.
Yeah, because when you do it in more right, there's compactness.
Yeah, so I
It's
will
easy.
just do that and maybe. So maybe in the next class I will do that. So again, both this. So super. And this is what see earlier when I wrote 1 upon mod x power n minus 2, there was no y, that y was 0, okay, but if I write it as 5 y minus x, I am going to write it as 1 upon y minus x. So depending on whether I want to consider my variable as x or y, I will get that Laplacian of g dx delta x or delta y. So we get kind of instead of means, because somebody may say your fundamental solution is giving point mass only at origin. What if I have it at other point, right? So this allows you to move around your domain. Okay? You can have measurement at the other point. I think this is what all I wanted to do today. Okay, I have probably finished early. At Henrik, if you can put that slide, penalization. So I will tell them.
Isn't that the lecture? Just open my lecture.
What?
Yeah, just close this.
Tell me it's loud. It will get recorded.
Of course.
Close this one.
Yeah, yes. Is this?
Just like it. Not this one.
Which one do you want?
Yes. Elliptic streets. Yeah. I will just talk about this part since the fixed point theory maybe I will do later on. So suppose he already showed, Henrik showed, right? He didn't show. He said that using fixed point theory solution to this particular problem will exist and you will have collection of functions v epsilon k, which is going to be solution of that particular differential equation. You also proved, so this minimum principle is same as what I called as maximum, right? You replace u by minus u. Okay? So you will get minimum principle just as we had maximum principle. So you can show that it is bounded. You can actually check. Okay? So I think it's a good exercise to go and see. Henrik, you will send the file, right?
You have the file.
Oh, you already sent it? No, this one.
Didn't I send you? You want it again?
No. So this is lecture 1. I will send it to them. I did not send the presentation file.
Do you have this one?
I don't know.
I forgot to send it to you.
At least for I think if you send me at the end of the day, then
I can send it to you.
yeah. So I will so that you can go back and revise it. Try to relate it to something that you read in your textbook and all that. So here minimum principle, you should try to check Why minimum principal? So bounded from above is straightforward because that is the way the function is defined. But minimum principal means we'll give you that it is bounded from below as well. And here you see this. So that because it satisfies that beta epsilon k of that particular function is Laplacian of the epsilon k, you get a bound on second derivative. Okay, Laplacian. So now independent weights by elliptic estimates give uniform W2P log intersection C1 alpha log regularity. Okay, for the epsilon k. So that part is again.
Maybe I can say something here. Because this is really
Because I was just going to take how to use Arzellas polyover. Yeah, that is what. So what happens is finally what you want to do. These were you are having two parameters, right? You have epsilon and you have k, and epsilon is going to go to 0 and k goes to infinity. You are having huge collection of function in some nice function space. Suppose you are in this function space. I will also tomorrow give you definition of what these function spaces are. So you all already know CK, continuous functions which are k times up to k times differentiable. You all know what is LP spaces. Okay, so here W2P spaces are like slightly bigger. Yeah, I think so, bigger spaces. No, smaller spaces. These are smaller spaces, but these are still going to be Banach spaces. So I will just define it. Most of the time we are going to work with L2, 2 variables, so which is actually going to be inner product space. Not only Banach space, they are going to be inner product space. Okay? So suppose these spaces are defined and you are looking at these collection of functions in these infinite dimensional spaces actually, right? And you want to take the limit of as k tends to infinity and epsilon goes to 0, and you want the limiting function to exist in the given space. And what is always, let me say, always going to help is Arzellas-Collet theorem. Because what happens? What is your Arzellas-Collet theorem say? Tell me. You have a collection of functions, continuous functions, which are uniformly bounded and equicontinuous. Right? Equicontinuity, right? What do you mean by equicontinuity?
The epsilon works for every f.
And any 2 points, right? For any f and any 2 points, right? So you have a collection of functions f of f, fn of x minus fn of y is less than equal to epsilon. For all mod x minus y less than delta, for all n. So delta is independent of your function, okay, and also of the points. Okay, that is what is equicontinuity. Yeah? So here, one of the ways uniform boundedness we will get from here itself. Okay, when you say C infinity regularity, you will get boundedness, uniform boundedness of the function. Anyway, you have shown. This part is there. If you get this one, okay, you will have elliptic estimates which will give you that the functions are uniformly bounded. To show it is equicontinuous, one of the best way to show something is equicontinuous is the mean value inequality. Okay, you have fx minus fy less than equal to mod of f dash theta times mod x minus y. If I know my f dash is going to be bounded, then I will get, if f dash is uniformly bounded for every f, then I get equicontinuity immediately. So here you see this is second derivative which is uniformly bounded. So I can use the mean value inequality for first derivative. Okay? So I will apply my Arzellas-Collet theorem to that. Okay? And once I apply the Arzellas-Collet theorem, I will get my V. So usually, like means when we are studying this Arzellas-Collet theorem, we never, means even I studied, I never knew what I am going to use it for. But this is where we will use for existence of the limiting functions which will solve your given problem, okay, in function space. And that is why remember, when you start with over here, I will define later, solution in weak sense. You don't know how regular it is. We could have just had LP or L2 or whatever, right? We require this C1 alpha. You require C1 alpha because you want actual convergence. You want to apply your Arjana's. So that is why you have two words. So many times for existence of solutions, that is where you have the difficulty. And this is the order you apply elliptic estimates, apply estimates, you try to find it, then you try to go to limit, try to find the regularity. That's how it is. So yes, I think that is the thing which I wanted her to explain, and you all should try to do this by using Arjana's. So that would be an exercise for you. Remember, a lot of things which are going to be given as exercise would be your assignment for your evaluation. So it's better you all note this and then spend time on it. So Henrik, I think I have said whatever I wanted to say for this. You want to speak about that, right?
Yeah, I just want to mention one thing that if you look at the PDE, so you should be careful here because the PDE is Laplacian of this, if you just call it P, is a function of this.
Yeah.
So this is not a linear function.
Yes.
So when you want to prove existence, it's not so obvious how to do that. This is far from a linear function.
That's what I was thinking.
So this is not linear. So you want to, let's say, durable problem, whatever you know, the methods. It's not, most of the cases not going to work. So that's the reason I'm talking with fixed point theory here. So you start, I mean, you can think of this in more simple form even. So I can write this as Laplacian of D is beta can be anything, or let's just write it as x, of x and v, because it looks like that anyway. We want resistance for this to see that if you could put, if you already had your function v, you could put it like this, and y here n minus 2, and you see that you sort of get the solution. Because Laplacian of this is going to be f. It's almost like your solution up to the harmonic function. The problem is that you don't know what f is, so this is not going to give you the answer. You cannot put it here and try to solve it. So what you can do is iterate method. So you start with a good guess, v0. So this is my solution. Well, no, it is not. So say, okay, let's solve this one. And v1 is not your solution. Then you say, okay, let's put v1 here, put 2 here, and then iterate this. Called j minus 1.
Yeah.
So you just do this iterative method and try to prove that there is a fixed point for this. And you can end up with that. And there's a limit. You need all the estimates and everything. So this is the way of doing it. Because it's nonlinear. It has the same linearity. You cannot just use any classical. Not two classical problems. Okay, so that was. So we start at 9 to 1, 9 to 1.
9 to
9 to I'm going to I'll send you a few names. It's not far to go to this place outside, the shops. No?
Sagar, you're staying on campus, right? Did you get your key?
No.
And Henry? He is staying on campus.
Okay.
Yeah, so maybe you can
Yes.
help him buy if you want to buy some.
It's just to buy something.
But he really is going to stay on campus.
How about the Wi-Fi?
Yes, that guy called
So,
the CBS guy,
this,
and he said that they are having some issues with their their Wi-Fi. So they are trying their best, but they are not sure. And so it's not only you; it is that entire place. It's not only for you. So he said we are trying to resolve. We are trying.
I will not have a Wi-Fi this evening,
But the university has.
but they are connected from this place.
Yeah, I think from most of the parts, the students know where it is.
So this
It will not be there in your hostel. Yeah, it will
it's
not.
not there.
It's not there.
Because so in the evenings I cannot. I have to push this. Thank you for your attention.
Thank you.
They're very talking.
Can we discuss a bit about tomorrow?
Yes, we can do that. I'm not going now. I was going to do some shopping here. Like if you're here, I can.
Yeah, I'm here.
So Luke is here. Are you here?
What was shopping later?
I'm not sure. Just drive to shopping.
You can go later. He is here.
But then I have to walk.
I will drive you. Don't worry. He is here.
But you will drive me? Because if you go, you cannot drive.
No, I will not leave you.
But I don't want to walk in this heat.
I will not leave you. Don't worry.
Yes, okay.
Because you want to go to your room and come back. Later, in how much time?
15.
15 minutes.
15 minutes, go back to this.
Yeah, he's up. I think next.
Good runner.
No, he will be in the next building.
Oh,
the building-
not in this place.
I don't know. In the next building.
Oh, okay.
Yeah, he's staying in the.
Was in this
He's
place.
staying in the next building.
Okay.
He's in the idol building. He has. So come tomorrow. Okay. So try to come on time.
See you later.
Try to read. I will also try to read. हाँ? हाँ जो भी उसने कहा वही पे
Maybe they're asking to turn off.
नहीं मुझे वो मेरे असिस्टेंट प्रोफेसर होता है तो मैं क्या करता हूँ थर्ड फ्लोर पर होता हूँ
वो जो भी है उसे बोलो और करो हाँ he said that we उसने already बात कर लिया है etc तो आपके साथ जो भी बात किया है वो do it हाँ don't take anything go and do whatever you want to do
फिर से आना है
We're going to take some coffee.
you want I will be So what do I prepare for tomorrow? Because as you see, I have done nothing today. At least not
For tomorrow, what is this? What is this?
That's the vegetable. He got for you.
No,
The few.
vegetable of
the what we had for lunch.
But just not brought this for you. It's a small
Oh, thank you.
sweet specialty.
Some sweet.
No.
ये क्या है? आप ले जाएंगे?